Many times when you are solving a free response question in AP Calc, what you want to look for are some keywords and phrases that are going to help you crack the question. And you're looking for things that you recognize, and you're looking for things that make you say, oh, that looks familiar. And the goal of this video is to try to help you to see some of those things. So this is a sample FRQ from a previous year. Hot water is dripping through a coffee maker. Gee, I wonder why Mr. Winter picked this particular video or this particular question of all of them to do. Imagine that, it's about coffee. Hot water is dripping through a coffee maker and it's filling a large cup with coffee. The coffee in the cup is given by the differentiable function c up above in the table, where c is measured in minutes and selected values are in the table below. Now, I'm encouraged by this because, as you can see, it looks like the volume of coffee is increasing as time goes by. Unless it was me, then the volume in the cup of coffee would be decreasing, of course. But in all seriousness, though, we can answer this question even though it doesn't look like we've got a whole lot to go off of. The first question in this is, use the data in the table to approximate C prime of 3.5. Okay, well, we know right off the bat that this is a derivative. And a derivative leads us to think that it's a slope, because, after all, derivative is just nothing more than the slope of the tangent line, as we all know. So if I'm approximating a rate of change for 3.5, then slope is an excellent way to estimate that. Now, how can I find the slope for something that isn't even on the table? Well, I'm going to recommend that we use this point and this point right here, because 3 and 4, midpoint of there on the x-axis, or the t-axis in this case, is 3.5. So I'm pretty sure that if we did m is equal to 12.8 minus 11.2 all over 4 minus 3, I got your back on the other one, no big deal. It looks like it's going to be 1.6. Now, it does say the magic words indicate units of measure, so this is ounces per minute. So make sure you throw those units in, otherwise they will throw a penalty flag on you for that one. All right, let's go on to part B and take a look at that one and see how we crack that. And we still have this same situation here, and it asks the question, is there a time between 2 and 4 at which C prime is 2? All right, now this, friends, is the mean value theorem, is really what it is. Because if you stop and think about this for a moment, remember, the mean value theorem says that at some point, assuming conditions met, we'll talk about those in a second, at some point, C prime of t is going to equal the slope of a secant line. Okay, that's our mean value theorem there. All right, now what conditions need to be in play for this to work? Well, the function needs to be differentiable, and the function needs to be continuous. Now, you would probably make an assumption that it's continuous on a closed interval, because even if there is no coffee in the cup, sad face, you still have the ability to measure how much coffee is in the cup at any given time. This function is not going to go undefined. And we also know from the prompt that it is differentiable. So having said that, we know that the conditions of the mean value theorem are set. So now all I have to do is I have to find the slope once again, but I'm going to use the points 4 and 2. Now, why am I using the points 4 and 2? Because that's the ones that are being signaled here in the question. So the slope is going to be 12.8 minus 8.8 over 4 minus 2, and you're going to get 4 over 2, which reduces to 2. So you can make the conclusion that since C of t is continuous on 0 to 6 closed and differentiable on 0 to 6 open, and the slope of the secant line going through t equals 2 and t equals 4 is 2, then yes, c prime of t will equal 2 in that interval. Okay, now I'm sure there's probably a much faster way of writing that out and maybe a little bit less verbose, but that's definitely something to think about. Okay, so now we found a way to crack that one. Let's go and talk about the next part here. Yeah, that kind of looks like my cat in the morning. You know, he's like, I want coffee. Well, he's not the only one. Okay, now this one is actually kind of a fun question because it asks us to do something that is really actually not a calculus task, believe it or not. It says use a midpoint sum with 3 subintervals of equal length indicated by the data to approximate the value of this. Okay, now hold on a second. Let's kind of crack what this means. The midpoint sum, this is really the MRAM method. And the MRAM method is used to estimate integrals. So what it's going to do is it's going to give us this right here. Okay, that's what it's going to give us. So what I want you to do for now is I want you to take this 1/6 and I want you to file it in your back pocket for the time being. And we'll come back to that in a little bit. Let's turn the focus on how we find the midpoint. Well, there's 3 subintervals of equal length, and we know that the table starts when t is 0 and ends when t is 6. So it makes a ton of sense that our intervals should go from 0 to 2, from 2 to 4, and from 4 to 6. So if I want to use midpoints, I have to use the midpoint approximation by using the middle points of each of those particular subintervals. Okay? So in order to do this, each subinterval has a width of 2. Oops, let's get the pen and not the highlighter. There we go. Okay, so each subinterval has a width of 2, and the first subinterval's height is 5.3. Then we have another subinterval of 2, and 11.2 is the height. Now, how do I know this? Well, again, picking those numbers up from the table right there. And then 2 times 13.8. Okay, now, unfortunately, this is a question where we have a hard time with this, maybe because you're not allowed a calculator. It is a number 5, boo hiss. You know, but here we go anyway. So this is 10.6, and this is 22.4, and then this is 27.6. So this is going to be a little bit challenging to come up with, but when you put it all together, it's 60.6. Okay, now, once again, that gives us an estimation of the definite integral from 0 to 6 of c of t dt. But what I'm interested in is 1/6 of this. And 1/6 of 60.6 is going to be 10.1. Okay, and specifically 10.1 ounces. All right, now we've gotten the what I would call the computational part done, and that wasn't too bad once you kind of cracked the code and figured out, okay, midpoint sum is MRAM. This right here is the integral only, but what's up with this 1/6? Because if we have this here, it's going to help us to explain the meaning. Well, if you take a look at that fraction of 1/6 that's on the outside, you might remember that the average value of a function is 1 over b minus a times the definite integral from a to b of that function. Okay? So this right here, what this entire expression that we're going to highlight in green to take care of the explanation here, this entire expression, that is the average volume of coffee in the cup over 6 minutes. Okay? That's the average value, the average volume of coffee. Now, how did I know that? Well, C of t is a function that gives us the volume of the coffee. And that's how I know that information. Okay, one last part to this question. Let's take a look at this. Oh, the coffee, but it's just too far. It's just out of reach. That's how I am some mornings, quite honestly. So I think we've all felt that from time to time. Okay, now the amount of coffee in the cup is being modeled by this particular function right here. B of t is equal to 16 minus 16e to the negative 0.4t. Using this model, find the rate at which the amount of coffee in the cup is changing. Okay, time out. Whenever we see these words, rate at which the amount is changing, a rate of change, altogether now, that's got to be a derivative. Has no choice. So I already know that before I do anything else, I need to find b prime of t. So to find b prime of t, we know the 16 drops out, and then this is where things get a little messy. I'm going to use the chain rule on this one. I have to sort of set this negative 16 to the side for just a moment because it is a constant. And the derivative of e to the something is e to that something. And then you multiply by whatever the derivative of that something is for the chain rule. So this is negative 0.4. All right, now this gets a little messy without a calculator. You may have to do a little side work, or it helps if you remember that 16 times 4 is 64. And then you can just sort of put a decimal point in the right spot. Okay? All right, so that takes care of that part, but you're interested in this amount when t is 5. You're interested in that rate of change when t is 5. So what you're really trying to find here is b prime of 5. So, 0.4 times 5, that's just going to be 2. So it's going to be 6.4 e to the negative 2, and that's going to be ounces per minute. That's the rate at which it's changing. Now, since you don't have a calculator for this problem, it is more than good enough for you to just stop right here and call it good. All right, so I hope you've enjoyed this, and in the meantime, this has motivated me. I think I'm going to go get a cup of coffee. Have a great day.